Hello everyone. Let's continue the discussion of the heart, and we're going to start with blood pressure. You remember this formula, P is equal to Q times R. If you remember, if that was a vessel, we said the amount of blood that is going to move from this point and get to this point, from point 1 to point 2, we said is equal to delta P divided by R, if you remember. Or we said P is equal to Q times R. This is the formula for one vessel. Can I expand this idea to the whole body? If so, I have to change pressure to mean arterial pressure. I have to change Q, which is the blood flow in this vessel, to cardiac output, and I have to change R, which is resistance for one vessel, to total peripheral resistance. And that is going to bring us to this formula. Some books, instead of mean arterial pressure, use PA as an abbreviation. The mean arterial pressure in average is around 100 units of mercury. The mean arterial pressure moves blood forward inside your cardiovascular system. This formula is pretty deceptive because it seems like if you increase TPR resistance twice, you expect based on this formula that your mean arterial pressure also is going to increase 2 times. But that is not going to happen. You have to understand, when you increase resistance, my cardiac output already is going to drop. Think about it. Here's my heart, and here's my aorta. If resistance inside the aorta goes up, my cardiac output already is going to go down, yes or no? Therefore, if my TPR goes up and my cardiac output comes down, my mean arterial pressure is not going to change that much. In fact, when your TPR increase twice, when it becomes double, this one is not going to increase double, it's going to slightly increase because cardiac output is already come down, and when cardiac output goes down, it's going to bring mean arterial pressure down also. So what I want you to understand is the relationship between resistance and mean arterial pressure, or cardiac output and mean arterial pressure, is not purely based on this formula because it would be misleading. With the same token, if my total peripheral resistance drops, do you think my mean arterial pressure is going to drop the same level? If my total peripheral resistance drops by half, do you think my mean arterial pressure is going to drop by half too? The answer is no, because when the resistance drops by 2, then your heart is going to pump more, your cardiac output is going to increase, and if this one is going to increase, my mean arterial pressure is going to go up. So if the total peripheral resistance drops by half, mean arterial pressure is going to drop, but not by half, it slightly drops. I said this one because I want you to understand the relationship between resistance, cardiac output, and mean arterial pressure is not as simple as you can see. It can be deceptive. Now, mean arterial pressure is a very important number because we said this is driving force. That if this is blood vessel, what makes your blood move forward? Is it systolic pressure? Or is it diastolic pressure? Well, the answer is neither of them. It is mean arterial pressure that's going to make your blood to move forward. So therefore, mean arterial pressure is a very important number. It's supposed to be around 100. When my mean arterial pressure is going to go above 100 or below 100, then I have to bring it back to normal because, again, that's a driving force for my blood. So therefore, my body should control my mean arterial pressure. How does my body controls my mean arterial pressure? How does my body make sure mean arterial pressure is going to stay around 100? Well, the answer is there are 2 ways. By baroreceptor reflexes. There's a reflex, it's called baroreceptor reflex. And the other one is called renin-angiotensin-aldosterone system. Let's talk about baroreceptor reflex. In the wall of the aorta, in the aortic arch, and in the wall of carotid artery, right where the carotid artery is going to bifurcate, is going to divide, we have stretch receptor. As soon as blood is going to come inside the, let's say, aorta, and aorta is going to bulge, that is going to send signal to the brain. So there is a stretch receptor in the wall of the aorta and in the wall of carotid artery. As soon as they bulge out, that means they understand there's too much pressure, there's too much blood. They're going to send signal to the brain. If the blood pressure goes down, then the wall is not going to stretch. And if wall is going to stretch less, they're going to send less signal to the brain. So brain understand the blood pressure drops because it's going to receive less signal, and brain understand that blood pressure went up if these neurons they send more signal. In another word, these neurons, they send a baseline to the brain. If they send less signal, that means blood pressure is dropping. If they send more signal, that means blood pressure is going up. So therefore, the number of the action potential that reach the brain would be important. Who is going to send this information to the brain? The answer is cranial nerve 9 and 10. This line that you see here is cranial nerve number 9. And this one that comes from the aortic arch is cranial nerve number 10. The set point here we said is 100. The mean arterial pressure of 100 is a set point. The blood pressure above that send more signal. The blood pressure below that is going to send less signal. But sometimes, people have hypertension. Why? Because it seems like either your medulla, the brain, is going to lose this sensitivity toward blood pressure, or the set point is going to move. So think about it. If medulla doesn't care about more or less of this signal, medulla is going to respond less to the number of signal that comes here, your blood pressure is going to go up without any response from your body. So that's why these people are going to have hypertension. Or sometimes the set point is going to change. Medulla is supposed to understand the blood pressure of 100 as a baseline. If your set point is going to change to 140, then anything above 140, your brain is going to respond. Anything below 140, brain is going to do nothing. So therefore, your set point may change, or you may lose the sensitivity to the signals. In a normal person, what's going to happen? In a normal person, this signal is going to come to the medulla in a place is called nucleus solitarius. Then medulla is going to do a couple of things. As you can see in this picture, carotid sinus, aortic sinus, is going to send information to medulla, and it's going to come to the nucleus solitarius. Nucleus solitarius is going to interpret this information and coordinate the activity of your sympathetic and parasympathetic nervous system. Inside the medulla, there's a center, it's called vasomotor center, and it's called cardiac center. Vasomotor center is the one that controls the resistance of your blood vessels, and cardiac center is going to control your heart rate and heartbeat. When the nucleus solitarius is going to receive this information, it's going to send this information to vasomotor and cardiac center, which is located in the reticular formation of the medulla. And then this reticular formation of medulla is going to control your sympathetic and parasympathetic. Now think about it. If your blood pressure is up, if these two neurons, they're going to send so many impulse, and your brain understand, hey, blood pressure is really high. What do you think your brain is going to do? What do you think medulla is going to do? Well, medulla is going to tell the parasympathetic, I want you work more, because parasympathetic is going to decrease your heart rate. Remember, when your heart rate goes down, then your cardiac output is going to go down. When the cardiac output goes down, as you can see here, your blood pressure is going to go down. So therefore, parasympathetic becomes active to decrease your heart rate. As a result, your cardiac output is going to go down. When cardiac output goes down, your blood pressure is going to go down. Also, medulla is going to tell the sympathetic, you have to slow down. Sympathetic is going to slow down. What's the function of sympathetic? Well, sympathetic usually is going to go to the heart and increase the heart rate. If sympathetic is not working, then the heart rate is going to go down, then cardiac output is going to go down. If cardiac output goes down, but blood pressure is going to go down. Sympathetic also is going to make your heart to contract stronger. And if your heart doesn't contract stronger, your stroke volume is going to go down. When the stroke volume goes down, cardiac output goes down. When cardiac output goes down, then blood pressure is going to go down. Sympathetic also is going to go to arterial. Remember, sympathetic is going to go to arterial and it's going to close your arterial. If sympathetic is going to slow down, that means your arterial is going to open up. If arterial opens up, that means your resistance is going to go down. When resistance goes down, the blood pressure is going to go down. And finally, sympathetic also is supposed to go to vein and squeeze the vein. If sympathetic slows down, that means your vein is going to open up. If the veins open up, this is vena cava, right? More blood is going to come to the right side of the heart. More blood to the right side of the heart, that means your preload is going to go up. When preload goes up, as you know, your cardiac output is going to go up. Remember Frank Starling law? When more blood comes to the heart is going to expand more. That means cardiac output is going to go up. When cardiac output goes up, blood pressure is going to go up. This is very important for you to understand how your medulla is going to control your blood pressure. And the last thing I'll tell you is, which of these two is more important, carotid artery or aortic arch? Well, the answer is carotid artery. Carotid artery is more important because this one can respond to higher pressure or lower pressure. Aortic sinus only responds when the blood pressure goes up. If you now take a look at this picture again, these two, cranial nerve number 9 and cranial nerve number 10, is going to bring the information to medulla. Medulla can send information to the, as you can see here, sympathetic nervous system. Sympathetic nervous system is going to come to SA node, AV node, and the muscle. So it can change the heart rate and can change contractility. Also, they're going to send information to parasympathetic. Remember, parasympathetic only change heart rate. And as a result, you can change your blood pressure. I put this picture also, which shows pretty much the same thing. In this slide shows if you have hypertension, what's going to happen. The cranial nerve 9 or cranial nerve 10 is going to send information to nucleus solitarius. Nucleus solitarius can go to the parasympathetic and tell the parasympathetic, I want you to work more. Parasympathetic is going to slow down your heart rate. Also, nucleus solitarius is going to tell sympathetic to slow down. As a result, sympathetic is going to come to the heart and it's going to decrease the heart rate and decrease contractility. But also sympathetic is going to go to the vessels and slow down vessel constriction. As a result, your arteriole is going to open up and your vein is going to open up, as we mentioned a few minutes ago. To make sure that baroreceptor reflex, what we explained, works properly or not, we do a test in the clinic. It's called Valsalva maneuver. By doing Valsalva maneuver, you're going to increase the pressure inside your chest and abdomen. Remember when you go and defecate, what do? You close your glottis and increase the pressure inside the abdomen. That's how you defecate. Well, the technical or medical terminology for that is Valsalva maneuver. So you tell the patient, I want you basically push as you do in the bathroom. So what is going to happen if you do Valsalva maneuver? When you increase the pressure inside the chest, here's your heart, which is inside the chest, correct? This is the chest. That heart is sitting, and blood is coming inside the right atrium. If you increase the pressure inside the chest, therefore less blood is going to get to your right atrium. If less blood comes to your right atrium, that means your preload is going to go down. If your preload goes down, that means your cardiac output is going to go down. And as soon as your cardiac output goes down, that means your mean arterial pressure is going to go down. Remember, we said P is equal to Q times R. So if the Q goes down, then P is going to go down. When mean arterial pressure is going to go down, we said your baroreceptor is going to detect that one. As a result, it's going to stimulate sympathetic, and as a result, your heart rate is going to go up. So remember, cardiac output is equal to heart rate times stroke volume. If your cardiac output goes down, we have to increase heart rate. Here's my point. You ask the patient to do Valsalva maneuver as if the patient is defecating. As a result of that, patient's heart rate is going to go up. You check the heart rate, goes up. As soon as patient is going to stop the Valsalva maneuver, you check the heart rate is going to go down. By doing Valsalva maneuver, I know if baroreceptor reflex works or not, because Valsalva maneuver is going to increase your heart rate, and by stopping this one, your heart rate is going to go back to baseline. And I know by doing that test, your baroreceptor reflex functions properly. I hope that makes sense. We said that to control mean arterial pressure, we can use baroreceptor reflex. This receptor is inside the aorta or inside the carotid artery, and those are called high pressure receptor because artery has a higher pressure. So therefore we call baroreceptor reflex as a high pressure receptor. The beauty of this one is this guy can control my blood pressure beat by beat very quickly. When you're laying down, you have a blood pressure. As soon as you stand up, the gravity is going to pull this blood down and your blood pressure is going to drop. Then baroreceptor reflex is going to kick in and bring your blood pressure back up. So baroreceptor is going to respond very quickly to change of blood pressure. This is for a quick response. This is not for a long term. In the long term, we're going to use kidney. Kidney is going to control your blood pressure in the long term. That's why people with kidney disease, their blood pressure is going to fluctuate dramatically because kidney is not working. To understand that, let's review one more time the kidney. We have a structure we call nephron. Here's one nephron, here's another nephron. This nephron is supposed to create urine, and urine of this nephron is going to come to this tube. It's called collecting duct. As you can see, the urine from this nephron also is going to come to collecting duct. So collecting duct is being shared by different nephrons. Let's make this one bigger. Here is my nephron. This is this nephron. And this is my collecting duct. Again, one collecting duct can get the urine from different nephrons. So this one is going to another nephron, this one goes to another nephron, this one goes to another one, and another one, and another one. So collecting duct can collect urine from different nephrons. So the way it works is, blood is going to come through this artery. It's called afferent artery. And this blood is going to get filtered inside the nephron. And nephron is going to clean up the blood. At the end of this nephron, you're going to have urine. The wall of this afferent arteriole is going to release an enzyme. It's called renin. These cells that release renin, also they have beta-1 receptor. So in the wall of this afferent arteriole, you have some cells. Those cells are called juxtaglomerular cells. And these juxtaglomerular cells, or JGC, they release an enzyme is called renin. And also those cells, they have receptor for beta-1. When you stimulate beta-1, you release more renin. Two things are going to make these cells, these JG cells, release renin. One is the pressure. When the pressure inside the afferent arteriole, this artery, is going to drop. When the pressure is going to drop, you release more renin. Or if you stimulate beta-1. What is going to happen if you release renin? We said renin is an enzyme. What is going to do? Well, take a look. If the pressure inside the afferent arteriole drops, then afferent arteriole is going to release renin. Renin is an enzyme, and this enzyme is going to break down a protein inside the blood. It's called angiotensinogen. This is the protein that we already have in the blood. Renin is going to break down angiotensinogen and change it to angiotensin 1. Angiotensin 1 is not active yet. It's going to go with the blood to the lung. In the lung, we're going to release another enzyme. It's called angiotensin converting enzyme. Angiotensin converting enzyme, or it's called ACE, is going to convert angiotensin 1 to angiotensin 2. Now we have angiotensin 2. Angiotensin 2 has multiple functions, and every single one of them is important. First, angiotensin 2 is going to go to your adrenal gland, and it's going to make your adrenal gland to produce aldosterone. Remember aldosterone from the endocrine section? When aldosterone goes up, aldosterone is going to go to principal cells of the distal convoluted tubule. I hope you remember distal convoluted tubule. Here's proximal. Here's a loop of Henle. Here's distal. It's going to go to this guy, and also it's going to go to this guy, collecting duct, and it's going to tell them, I want you to absorb all the sodium. I don't want you to lose any sodium. I want you to take sodium out. As a result, your urine is going to have less sodium. So this wall and this one, they're going to start taking the sodium out. And you know, when the sodium is taken out, water is going to follow sodium. So therefore, water is going to get out. As a result, you pee less. So aldosterone is going to remove sodium. As a result, it's going to remove water, so you pee less. If you pee less, that means you're keeping more water and sodium in your body. That means your volume is going to go up. When your volume goes up, your pressure is going to go up. As a result, the pressure here in the afferent artery is going to go back to normal, and the release of renin is going to stop. So did you see what happened? The pressure inside the afferent artery dropped. As a result, renin was released, and renin is going to make you to absorb sodium and water. So as a result, you pee less. That means you keep the water in your system. Therefore, your blood pressure is going to go up. That's the first function for angiotensin 2. The second function for angiotensin 2 is this. Angiotensin 2 is going to go to the proximal convoluted tubule. That means it's going to come to this tube now. Let's say this is a cell of PCT. This is one cell in the proximal convoluted tubule. Let's say this is the lumen that urine is going to create at the end, and this is your blood. The PCT is going to come here, and normally is going to dump hydrogen inside the urine and remove sodium as a co-transfer. And then this sodium is going to come to the blood. Remember, when sodium is going to come, water is going to follow the sodium also. Also, PCT is going to dump bicarbonate inside the blood and make your blood to become more alkaline. Now think about it. Angiotensin 2 is going to come to this guy and is going to empower this one. So as a result, this pump is going to work more. If this pump works more, that means you're going to take more sodium out. That means you're going to take more water out. That means you're going to dump more potassium inside the blood. So therefore, I would say another function for angiotensin II is going into PCT, increasing the absorption of the sodium and dumping hydrogen inside the lumen. Increasing your sodium reabsorption is going to increase more water reabsorption. As a result, your blood pressure is going to go up also. Angiotensin II also is going to go to hypothalamus. Angiotensin II is going to go to hypothalamus and stimulate the thirst center. As a result, when you're thirsty, your hypothalamus is going to produce more antidiuretic hormone. And you remember, antidiuretic hormone is going to affect your collecting duct and take the water out. By taking water out, that means you pee less. As a result, your blood pressure also is going to go up. And finally, angiotensin II is a vasoconstrictor. By constricting the vessel, resistance is going to go up. As a result, the pressure is going to go up. Therefore, as you can see, by releasing renin, you create a bunch of system to increase your blood pressure back to normal. So if you remember, we said a few minutes ago, to control blood pressure, minute by minute, beat by beat, we're going to use beta-receptor reflex. And in the long term, we're going to use this system. That's why it's called renin, angiotensin, aldosterone system. Are these the only way to control blood pressure? The answer is no. The other regulatory mechanism are three of them. One is the chemoreceptors, another one is ADH, and the third one is called cardiopulmonary beta receptors.